come back to the second half of this lecture. We just now proved a theorem which characterizes when the sum of subspaces is a direct sum. Immediate corollary for this, let me note it down. U, now it is only for two subspaces U and W, two K subspaces. Of a vector space V. Then the sum U plus W is a direct sum if and only if U intersection W is 0. There is only one condition now, U intersection W is 0. In this case, U plus W is written is like this, U plus W, isomorphic actually. The map we have defined in this direction. The map defined in this direction is U comma W is mapped to U plus W. This map is clearly surjective and this condition means it is injective. And this is because of this, then the dimension of U plus W is dimension of U direct sum W, which is then dimension U plus dimension W. So, that now leads to a definition which says that definition, if V is a direct sum of U and W. What does this mean? This means two things, V equal to U plus W, the smallest subspace which contain both U and W is V, and U intersection W is 0. So, therefore, any element V in V has a expression U plus W, where U and V, U is in U, W is in W, and U and W are uniquely determined by X by V. In this case, we will say that W is called a complement of U in V. Now, note that for any subspace there is a complement. So, let me note that in the next page. So, note that every subspace, every K subspace U of V has a complement in V. Why? Proof is very simple. What you do is you take a basis of U. So, U1, U2, U are basis of, this is a basis of U. And extend by adding few more vectors, extend it to a basis of V and extend W1 to Ws, K basis of V. And take the W to be subspace generated by W1 to Ws, that is W is K W1 plus K Ws. And because the W's are linearly independent, this sum is same as the direct sum. And also it is clear that U direct sum W is V. First the sum is V, that is clear because this is a generating system for V, and it is direct because nobody is in common, because it is a basis. If there is a common element, on one hand it will have a K linear combination between U1 to UR, On the other hand, it will be K-linear combination between W1 to Ws, but they cannot be equal unless they are 0, because otherwise it will give a dependence relation among these bases. Okay. So, however, this complement W is not uniquely determined by U. There, for a given subspace U, there may be many complements, because this is not the only way to extend it to a basis. There are many ways to extend it to a basis. For example, you can also do it to this basis, you can add U1 to them. This is also will also be a basis of V. If this is a basis, this is also a basis. The number is correct and generality is also correct, so that is a basis. So, there are many ways to get a complement of a subspace in a bigger space V. Okay. Okay, so now let me define. First, let us start with an example, and then that we will define formally what projection is. So, let us consider suppose to understand, let V is the direct sum of two subspaces. Remember, this means V is the direct sum of U and W, and U intersection W is 0. That simply means that any x in V has a unique expression x equal to U plus W, where U in U, W in W, and uniquely determined by x. Uniquely determined, that is very important. So, I define a map now from P. P is a map from V to V. What is the map? Take any x and write x as U plus W. U is in U, W is in W, and they are unique, because we are assuming this, and map these to U. Look at this map. First of all, I want to say that this map is well defined. Well defined simply means that if x has another expression and whatever you are taking that one should be unique, but that is because it is uniquely determined. This map is well defined, and also P is K-linear. That is, what we have to check is, if I have two elements x and y, then P of Ax plus By equal to Apx plus Bpy. This is why what we need to check for all scalars AB and for all vectors x, y in V. So, start with x, y in V and write x as U plus W, where U is in U, W is in W, unique. Unique is very important. Similarly, y as U prime plus W prime, U prime is in U, W prime is in W, and unique. So, therefore, by definition, RHS is nothing but A times U plus B times U prime, that is RHS. What is the left hand side? LHS is, first I have to add this. So, when you add and collect the elements in U together, so P of Ax is A times this. So, that is AU plus AW. I have written it apart because I want to collect. So, here it is U prime and times B. So, plus BU prime plus B W prime. Now this is in U because U is a subspace. This is in W because W is a subspace, and because this sum is direct, they will be uniquely determined by X and Y, because U is uniquely determined, U prime is uniquely determined, W prime are also uniquely determined. So these are uniquely determined. So by definition of P, this is nothing but the first component, that is AU plus BU prime, but that is also RHS. So that checks the linearity of P. So such a map is called a projection. So let us formally define. So definition, a linear operator K linear operator, if one want to be specific, P from V to V is called a projection of V if P square, which is P compose P, is P. In the earlier map, I just forgot to check here this map. Please note that if I compose P with P, I will write here P compose P is P. Let us check this orally in this example, because I have to check that for every x both the sides is evaluated at equal. So P of x is by definition that U. What is, once more if I apply P, because U is already in U now. So the unique decomposition of U is U equal to U plus 0. So therefore by definition of P, P of U will be U. So that checks P compose P is P. Is it clear? So therefore it is worth considering in general K linear operators on a vector space which has this property P square is P. P square is by definition P compose P. Okay, so what does this mean actually? What are these operators? You remember we want to study this K algebra and KV. This is a K algebra. Multiplication in this K algebra is nothing but the composition of maps. So this is a K algebra, and in this K algebra these are P. P is by definition P has to be here, and this condition means there are idempotent elements in this K algebra. So P is idempotent element in the K algebra endomorphisms of V, idempotent. More generally, if you have a ring R plus dot, if this is a ring, and R may not be commutative, maybe not commutative. So with respect to plus, the ring is very good, because addition in the ring is good because it is an abelian group. So all invertible, that all properties are there. To study ring, what is very interesting to study is the multiplication, what kind of properties multiplication has, whether it is commutative, what are the units, and these elements are special elements, they are idempotent elements. Idempotent means x in the ring is called idempotent if x square is x. So now let us try to draw the pictures. So now picture, I want to draw a picture and show it is convenient. So now we are still considering V is U direct sum W, and the projection here P is V to V, and the map is clear. X, write X uniquely as U plus W and map it to this U. U is in U, W is in W, and these are uniquely determined by the given vector x. And if you compose once more, this u goes to u by definition of P. So, P square is P. This is also called more specifically, one can call it P is projection onto U along W. I want to use this expression. U is the image, and so this I am calling because U is nothing but the image of P, which is all those x in V such that Px equal to P, Px equal to x. But this is also same, inside thing is also same as if you shift x to the other side. This means, let me write this, this is also same as the kernel of identity on V minus P. See, this is also linear map identity minus P, and what is the kernel of this? All those x in V, so that this ID V minus P on x is 0, but that is same as this equation, because we shift ID to the other side. So, how does one draw a picture? So, this is my U, this is my U, and this is my W. So, this is U and this is W. Also note, this W is what? W is the kernel. W is kernel P. Where will if x is only W, then it goes to 0 because it has no U component, and expressions are unique, that is very important. So, this direct sum, being a direct sum, is very important. We cannot do this for an arbitrary sum. So, if I have say x, arbitrary x here, which is U plus W, then what will be P of x in the picture? It will be this. This is P of x, which is nothing but U. This U is image P. W is kernel P. Okay. This is 0 here. They intersect in 0 only. You see, the picture is clear. This is if y is here, this is x. Y is here. This is y. You can think of this is y. What is P of y? P of y will be somewhere here. This is P of y. So, all the elements go to U from V. And this is so. This is a standard picture. So, this is I did not draw perpendicular for the reason because we have no concept of perpendicularity. But if you consider, for example, V equal to R2 and you take U equal to x axis, that means what? This U is, that means V cross 0, R cross 0. R cross 0, that is x axis, and W equal to 0 cross R. Now, note that V is a direct sum, V is which is R2, which is the direct sum of U direct sum W. That is because it is a sum first, that is clear, and they do not have anybody other than 0 in common. So, this is u and this is u and this is w. Now, it is perpendicular because we have that we have a inner product on R2, which I talk about inner product we will see. Then we can talk about orthogonality, perpendicularity and so on, but in general in a vector space we cannot talk about perpendicularity. There is no measurement for perpendicularity. So, when we do inner product spaces, precisely we will introduce a tool which will measure perpendicularity, which will also measure a distance and so on. Right now in arbitrary vector space we do not have these tools. Okay, and then if this is in standard notation it is u comma w, but then one could also write this as u plus w, because when you write this the pair, when you write it u comma 0 plus 0 comma w, and you are identifying u with this 0 u comma 0, similarly w as 0 comma w, and so that justify why we are writing u plus w. And what is the projection onto u? That is precisely this u, and onto w it is this one. And if you have taken the first projection V2 R2 to R, u comma w going to u, this is the first projection, and the image is precisely the x axis and kernel is precisely the y axis, right. We could do the other way also, you can project it onto the y axis, but these are complement to each other. So, I will now define. So, let us continue. Now, start with the projection. So, P is our projection from V to V. Projection. Remember, I don't have a decomposition of V as a direct sum, but I am going to get from the projection. So, what is the projection? Projection is simply a k-linear map from V to V with the property P square is P. So, and we have seen if P square is P, then I am calling U as image P. I am imitating the above concrete example. So, what is that? This means all those x in V such that x equal to say P y for some y, right, that is the image. But you see, you do not have to write so complicated, because when I apply once more P, what happens? Then Px is equal to P square y, but P square y is Py, because P square is P. Therefore, I could have simply written Py as Px. So, instead of thinking such this thing, I would simply replace this by x equal to Px. So, that is the image P. Okay. So, therefore, the image, so then in our definition, remember we have said that P is a projection of V onto its image, right. So, but image is U, onto U, okay, this is image P. Now, I want to write along whom? Along the kernel, kernel P. So, what is kernel P? Kernel P is precisely all those y in P, y in V such that P of y is 0. But if P of y is 0, again I will do the same thing, I will apply P once more. So, what will I get? P square y, which is Py, which is 0, So, that will not give much, but I want to also note that look at the new linear map which will come from P, which is IDV minus P. Let us call it Q. This is also linear map from V to V, because we know linear maps can be added. Set of linear operators is a K algebra actually. So, I can add, multiply by scalar, and composition is the multiplication. So, I want to test whether this Q is a projection or not. So, I should compute what is Q square. So, Q square is by definition IDV minus P composed with IDV minus P, and we have to be little careful here because the composition is not commutative. So, do it slowly. IDV compose IDV is IDV, then IDV times this minus P, that is minus will come out anyway, minus IDV compose P, that is P. The next one is minus P times IDV, that is minus P again, and minus P times minus P compose minus P, that is minus will become plus, and P compose P, that is P square. Simplify this. This is IDV minus P, and this P square is P again, and that will get cancelled with one of them. So, you get this, which is nothing but Q again. So, this Q square is also projection. So, Q square, what we have proved is Q is also projection. Q is also a projection of V, and along whom? Along the image. So, I have to find image of Q. Image of Q. What is image of Q? Let us find that. So, that means all those x in V such that I limited this, because you already said it is a projection. The x is Qx. But what is x is Qx? X equal to Qx means what? Qx we know, that is IDX minus P. So, this Qx is x, ID evaluated at x is x minus P of x. So that means this is precisely what? Did I make a mistake? Okay, so this means no, there is some mistake somewhere. X is Qx. So you cancel x from here. So you will get this is equivalent to saying P of x is 0, but that is equivalent to saying x is in the kernel. So this image Q is nothing but the kernel P. So therefore, we have two P and Q are projections, but they are not independent, they are related to each other. So this Q is called, a complementary projection to P, complementary. And we have proved the following actually, and this will actually this projection will give you a direct sum decomposition of V. So let me write in the theorem form. So theorem, so let P from V to V be a projection. Projection again, let me repeat, it is K linear K-linear map, K-linear operator, and with the property that P square is P. Then there is a direct sum decomposition for V. V equal to image P direct sum kernel P of V, and P is the projection of V onto image P along kernel P. So, what do we have to prove? We have to prove that V is, so proof, we need to prove two things. V should be the sum of image P plus kernel P, and the intersection of image P and kernel P should be 0. That is the meaning that it will be a direct sum. So, first I will prove that every vector in V is a sum of somebody coming from image P and somebody coming from kernel P, and also I will prove the kernel this is 0. So, let us prove that. So, start with any vector x. I want, it is clear that x is, so I want somebody in image P. So, that is obviously I will take Px, and I want somebody in the kernel. So, plus x minus Px. Now, we need to check that this is in image P, this is what we need to check, and also we need to check this is in kernel P. That will give us a sum, and we will worry about this the next part. So, visibly this Px is in image P because it is P of somebody. Now, I want to check this is in the kernel P, that means when I apply P to this it should become 0. So, apply P to this x minus Px. P is K-linear, so it is P of x minus P compose P is P square of x. But P square is P because P is a projection. So, this is Px minus Px, which is 0. So, indeed this is an element in kernel. So, we have written every vector in V as a sum of sum of two vectors, one is in image P, the other is in kernel P. Now, we want to check there is nobody in the intersection other than 0. So, suppose there is x, if there is x in the intersection image P intersection kernel P, then what happens? Then because it is in the kernel P, P of that should be 0, P of x should be 0 because we are using the fact that x belong here. Now, I want to use x belong here. So, that means what? That means x is P of somebody, x is P of y, but P is P square, which is also P square of y because P is P square, but P square is P of Py, but Py is x. So, this is Px, but x is in the kernel, already we have checked x is, we are assuming x is in the kernel. So, Px is 0 because x is in the kernel. So, that checks that if it was in kernel as well as image, then x has to be 0. So, that proves that this is a direct sum. Once it is a direct sum, then what is P goes? P goes exactly to, P is exactly the map which sends x to P of x. So, that is, so this decomposition tells you this is u and this is w, and the map P is definitely x going to u. So, that is precisely the projection along u and along U, no onto U and along W. So, a typical picture, you see what we draw picture was in R2, the picture of this was U and this is W. So, you are projecting onto this axis along this W. So, when you talk about projection, both the subspaces are very important. One, the image got into that, and the other also the direction is also directed by that W. More, this will become more and more clearer when once we bring a geometry into the picture, that is one thing. And also now the next time I want to do not one projection but several projections, and then we will get decomposition of a vector space into the UI, now family UI. So, that is what we will do it next time. Thank you.